Hello, we are going to be able to transform a linear monosaccharide into a Hayward projection and finally into a chair conformation. Now, this portion, sometimes students find it challenging, especially because it involves 3D structures, but I want to give you a simple way of doing the transformation. So let us start from glucose. So if we use glucose, if you want to transform it into a Hayward projection, the first thing is to sketch the Hayward projection skeleton. And the way I'd want you to look at it is, assume it is like a table. So this bottom part, let's assume you are sitting on a dinner table and you are sitting on this other side, which is bold. So the other portions are kind of going away from where you are sitting. And after that, we draw lines that join the carbons through the center. And we need to label them. So let us start from the starting material. So this material here, if we look at it, this is going to be D-glucose because the OH at the bottom is on the right. And when it's on the right, we label that as D-glucose. If this is glucose, if it was like galactose, we'd call it D-galactose or whatever the monosaccharide is. So in order to transform the linear compound into cyclic structure, we know that there is need to use a base to deprotonate the OH at carbon number 5 so that we can use the lone pairs of electrons to attack the carbonyl, which will later on pick a proton. So that means the OH at carbon number 5, let us label them so you can see the carbon number 5. So 1, 2, 3, 4, 5, and 6. So carbon number 5 is no longer going to have the OH because we have used that oxygen to generate the hemiacetal. So in a hemiacetal, we're going to have an OH. Can have an OH here. That is the one at carbon number 1. So let us label this as well. 1, 2, 3, 4, 5, 6. And carbon number 6 has an OH. So carbon number 1 is going to pick a proton and transform into an OH. And that OH, because we have messed up with the stereochemistry there, it could either be up or down. So we could also have another one where we have introduced a stereochemistry from the carbonyl that did not have a stereochemistry before. So now it could be either up or it could be down. When it is down, we call it the alpha. When it's up, we call it the beta position. So now it's going to be transformed into beta D glucopyranose. That is, we have transformed the glucose into a 6-membered ring, or we could have alpha D glucopyranose. Pyranose simply means a 6-membered ring. The other positions still remain the same, so 1, 2, 3, 4, 5, and there's going to be 6 over here connected to an OH. And we're going to have those lines joining each of them. The next thing I want you to look at very keenly is how we are going to allocate those OHs on on each position, whether it's going to be up or down. So let us start from carbon number 2. We have already determined that for carbon number 1, the OH could be either up or it could be down. Now, going to carbon number 2, the OH is on the right. Whenever you have OH on the right, it's going to be down. So for number 2, OH is down. For number 3, OH is on the left. When it's on the left, it's going to go up. That's the conventional way to do it. When you have OH like in position 4, it's on the right, so it's going to be down. This goes up. Hydrogen, everything that is left, we just fill it with hydrogen, hydrogen, hydrogen. And for the positions 2, 3 all the way, there's no change, so we just copy what we had in the beta D glucopyranose into the alpha D glucopyranose. So OH, H, OH, H. So we have transformed the linear glucose into a Hayward projection. Now we can call it either beta D glucopyranose or alpha D glucopyranose. Next, I want us to be able to transform this, the linear, or we can either do it from the linear glucose or from the Hayward projection. We can transform that into a chair conformation. The first thing I want us to do is to review some stuff that you might have already done in Chem331. And that is how to determine the equatorial and the axial position. So assuming we have position 1 here, let us label this 1, 2, 3, 4, and 5. So what we could do is we can have an axial position. Axial positions are going directly up or down. So usually we can have them alternating. Down, this is going to be up, this is going to be down. Those are axial positions. This is going to be up. And then the equatorial positions, we are going to have them projecting towards the sides. So this is going to be an equatorial position, equatorial, 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 equatorial. Could have equatorial position over there. So equatorial positions are projecting towards the sides, and the axial positions are either directly facing up or directly facing down. This is an axial position over there. Okay, so if you want to transform a linear glucose into the chair conformation, we can first of all do it from linear glucose to the Hayward projection, and then we directly transform that into the chair conformation. The conventional way is to start from 2 parallel lines. again 2 parallel lines and have oxygen towards the top right. And after that, we are going to put the OHs either up or down depending on where they are. So mostly you just do an eyeballing. So let us say we start from carbon number 1. Let's label them first. So this is 1, that's going to be 2, this is going to be 3, 4, that's going to be 5. So 1 again, 2, 3, 4, 5, and we also have 6. So what we are going to do is to look at what we made in the Hayward projection. Starting from position 1, the OH is up. There are only 2 possibilities for position 1. We can either have it that way or that way. So the equatorial position is going to be up, the axial in this case is down. So OH and H. When you go to carbon number 2, the hydrogen is up, which is the equatorial, the axial, and then the OH is down, which is going to be in the axial position. Carbon number 3, we have 2 possibilities, could be equatorial or axial. So the axial is down, so that is hydrogen, this is up. For carbon number 4, the one that's going to be up is going to be axial, down is going to be equatorial. And whatever is up here is hydrogen, whatever is down is OH. And we can do the same with the alpha D glucopyranose. For carbon number 1, we can have axial or the equatorial. For equatorial, we have hydrogen, which is up, OH is down, so that is the axial. Position 2, we have hydrogen, and then we have OH in the equatorial. Here we're going to have that, and then so we can just copy them because it's only position 1 that differs. So just copy them from what we did in the beta D glucopyranose, and we form the product that looks like that.